morning, students. Now in this class we are going to see the topic applications of eddy current. Before entering the topic, I like to revise the meaning for eddy current and the demonstration also. What is meant by eddy current? Eddy current is the current produced in a metal when the metal is moving in the uniform magnetic field. The current produced in the metal in the form of closed loop, we called it by the name of eddies. So that current is called as eddy current. The eddy current, it can be produced when that metal is moving in the uniform magnetic field, or the metal is a static one and you are applying a varying magnetic field, it produces the eddy current. See the PPT board. Fourth chapter, electromagnetic induction and alternating current. The zip file. Here the metal, that brown color, that is a metal, and now you are moving that bar magnet closer. That bar magnet is moving towards that metal. So that red color dot in the metal is called as a induced current or eddy current here. So when the bar magnet is moving closer to the metal, so magnetic field linked with the metal, it will be vary, so flux changes, so eddy current is produced in the particular metal. So after some time, when that bar magnet is very closer to that metal, we kept that bar magnet is a static one. So metal is a static, bar magnet is a static. So at that time there is no red color dot line in the metal. That means no eddy current produced in the particular metal. So the eddy current, it will be produced only you varying the magnetic field, or otherwise in a uniform magnetic field the metal is in a motion. That time only we can produce the eddy current. Next, demonstration. Already I gave the outline of the demonstration method. How will you produce that eddy current? See the diagram. At the first diagram, part A, the circuit is a open circuit, so there is no current flowing through that particular metal, so no induced current, no eddy current. So that suspended metal, it can be slide over in between that electromagnet. So that blue color and red color, it acts as an electromagnet when you are applying the electric current to the metal. So without any current passing through that metal, that suspended metal, it can be easily slide over in left and right direction. So that angle of deviation, the swing angle is maximum. See the second case, the circuit is closed, so that suspended metal, it also oscillates in between that electromagnet, but that angle of swing, it will be less compared with the first case. That angle of swing in the second case is very less due to the opposing of eddy current. So eddy current, it always opposes that which is causes to produce it. And see the third case, third diagram, we are using the metal. It's a strip, single strip. In between that metal, we make a small hole. So if you are using this type of metal, definitely this type of metal, it reduces that eddy current, because the eddy current is nothing but it is a closed loop. So if you make any holes or any partition in the particular metal, definitely it will be affect the path of flow of the current in that particular metal. So it reduces that eddy current. So next one, how will you reduce the eddy current in any one of the metal? So already I told that there are two things are there. The first one is, for using thick metal, alternately we can use that thin laminated sheet. If you are using thin laminated sheet, it will be reduce that eddy current in the material. For thin laminated sheet also we can use two different types. One is single lamination, each rectangular strip combined to form a core, or otherwise we are using that E and I shape laminated core. After combining this E and I, we have the single strip. So compare with the first single lamination, that E and I lamination also reduced more amount of eddy current. So this is the first method. By using thick metal, it produces enormous amount of eddy current. By reduce that eddy current, we are alternatively using that thin laminated sheet. And another one alternative way, you drill a small hole in the thick metal. Small hole, make a small hole in a thick metal, it also reduces the eddy current. Our next topic is applications of eddy current, or uses of the eddy current. That eddy current, we are using more devices. In your textbook, they are focusing only a few points. The first point is deadbeat galvanometer. Deadbeat galvanometer. The galvanometer is a device used to measure the electric current passing through the circuit. So when the current is flowing through the circuit, the galvanometer pointer, it shows some deflection in any one of the side. Deadbeat galvanometer means that the pointer, it comes to rest at any of the position, cannot accelerated into equilibrium point. With respect to equilibrium point, it cannot be accelerated a long time. It comes to rest to any one of the position immediately. So we called it by the name of a deadbeat galvanometer. See the diagram. So that metal, it placed in between that U-shaped magnet. When the eddy current is produced, so that production of the eddy current, that pointer, it slide over through the scale. The pointer, it is pivoted at that small size of the magnet. See the explanation for the case. The coil of moving coil galvanometer, which is used to measuring the current. When the current is flowing through the coil, gets deflected and oscillates about its equilibrium position. Like the simple pendulum case, if you applying a force to the simple pendulum, the bob, it will be accelerated with respect to the equilibrium position. When the eddy current is produced, because the metal is accelerated in between that magnet, so eddy current is generated. So that generating eddy current in the metal frame, it opposes the acceleratory motion. So that pointer which is connected with that metal, it comes to rest immediately. So we call it by the name of deadbeat galvanometer. And second one is induction furnace. So that inductance furnace, this device used to produce an enormous amount of heat to boiling any one of the material, or if you want to melt any one of the metal or any devices, we can use that induction furnace. So the stove, induction stove and induction furnace, that devices used to produce enormous amount of heat energy. So in this stove, at a particular point, it produces an eddy current, and the same place you kept that vessel. So the vessel is some of the vessels only using for induction stove. Not all the vessels cannot used in the induction stove. So if you kept that particular material vessel in the induction stove, on the induction stove, immediately enormous amount of heat energy is produced due to the variation of the flux. So it easily boiling the water, or we can easily cook it. In induction furnace also it produces high frequency, high magnetic field variation in a fraction of a second. So it produces very large amount of eddy current, and that eddy current is used to generate a heat energy. That heat energy is sufficient to melt quickly any of the metal. So that is the use of eddy current in the device induction furnace. Next one, electromagnetic brakes. That brake we can apply in all the vehicles, especially we are using that type of brake in electric train, and bike also is working on the basis electromagnetic brakes. So the axle of the train is surrounded by a coaxial cylindrical drum. So we have the drum and we have the fixed magnet. When the drum is rotated, in between that bar magnet, fixed magnet, metal rotated in a magnetic field, so it produces a variation of magnetic field. Flux is varying, so it induces the eddy current. That induced eddy current is opposite the relative motion between the stationary field and that rotating drum. It opposes the relative motion between that two things. One is stationary field, another one is a rotating drum. So that's why the train is slowed down and comes to rest quickly and smoothly. So that electric brake concept also working in the electric motors, like the fan also is working on the basis of that electric brakes. Next important one thing is eddy current testing. It is one of the simple non-destructive testing method to find a defect like surface cracks, air bubbles present in a specimen. If you are build any one of the new vessels, machines, or any one of the specimen, you are going to check that the specimen is don't have any defect. For that purpose, we can use that eddy current. The presence of defect causes the change in phase and amplitude of the eddy current. Already in the beginning of the lesson, I told that the method to reducing the eddy current. If we drill a small hole in the particular thick metal, definitely it reduces the eddy current. So if any of the defects are there in that specimen, definitely the path, that circular path, the loop path of the eddy current, it will be changed. So due to the changing of the path of the eddy current, we can analyze it. This specimen is not a good one. It has some defect in that particular point, and also we can measure that size and shape of the defect also with the help of the eddy current. See this one, crack detection. This is related with the last topic, eddy current defect method. So see the first diagram. Without any defect, that circular path, concentric circle path is the direction of flow of the eddy current. So there is no change in the path. It actually says a concentric circle. And see the second one, if we have any cracks or any defect, so at that place the eddy current path, it will be changed. So that causes produce in that particular metal. So using that path change, we can analyze the defect size and the strength. Crack detection is one of the primary uses of eddy current inspection. Okay. Next one, induction motor. Already I told that the induction motor, for any type of the motor like the fan and any of the motor, it is also working on the basis of eddy current. So at whatever may be, if any of the places, if you want to oppose which is causes to produce it, At that places, the eddy current plays a main role. In induction motor, it consists of a long metallic axles mounted lightly in a uniform magnetic field with its axis at right angle to the field. If the magnetic field is rotated with respect to the stationary axle, here the magnetic field is rotated, but the drum that axle is a rest. So that time also the eddy current is developed in it and it reduces the relative motions. So if you switch on the fan, initially the wings on the fan, it moves very slowly because the steady current, it opposing the motion of the wings. So that opposite force is greater. So that's why that wings is moving slowly at the beginning. So after a particular time, the speed of the wings is overcome that opposing force. So it is moving a higher speed. After a particular time, if you switch off the fan, so the fan speed it will be reduces. Within a fraction of second, the wings it comes to rest due to the eddy current. Next one, speedometer. That function of the speedometer is also like the deadbeat galvanometer. The speedometer, it is a device used to give the speed of that vehicle at that particular instant. We can measure the speed of any of the vehicle with the help of the speedometer at that particular instant. So in a speedometer, the magnet rotates inside the pivoted metallic drum. We have the metallic drum and the magnet. Here the magnet is rotated. So the speed of the rotation depends on the speed of the vehicle. After explaining the statement, I will give the diagram representation how the speedometer is working. And due to the eddy current in the drum, it causes the magnet to rotate within the drum. It rotates through an angle with its proportional to the speed of the vehicle. So the pointer, it will be rotated. That rotation is proportional to the speed of the vehicle. See this one. See the GIF file. So the magnet is rotated. So the shape of the hairspring, it will be changed. So due to the change in the magnetic flux, the pointer, it's deflected from the 0 to the particular speed. That speed, it gives the speed, it is proportional to the speed of the tire vehicle. See this one also. So that a tire is attached with a cylindrical drum. When the tire is rotated, that cylinder is also rotated. So here at the bottom, the rotation of that cylinder, the magnetic flux linked with the drum, it will be varies. So the polarity, it will be varies. So due to this variation of the flux, the torque is produced in the pointer. So the pointer, it gives the actual speed of the vehicle. Next one, drawback. We discussed that positive side of the eddy current. Now we are going to enter that drawback of the eddy current. There are very few drawbacks are there. The main thing is heat loss. When the eddy current is produced in any one of the metal, it is due to the variation of the magnetic flux. So the variation of the magnetic flux, that variation, it cannot be totally converted into the eddy current. The minimum amount of energy, it will be lost in the form of heat. So there is a major heat loss during cycling eddy current due to the friction in the magnetic circuit, especially where the core is situated. There is a loss of useful electrical energy in the form of heat. So most of the energy, it will be lost in the form of heat. So remaining energy only, it is converted into the useful electrical energy. So main drawback, main negative side is a heat loss. And second one, if you want to transfer that energy, that useful electrical energy from that particular material, particular metal to another one metal, it is also difficult. And one more thing, the magnetic flux leakage is also possible. Flux leakage means if the flux linked with the primary circuit, that entire flux, it does not linked with the secondary circuit. If the eddy current is produced in the secondary circuit means it is nothing but we have the two different coil. You are applying a current in the first coil, it is a primary circuit. That eddy current is produced in the secondary coil, second coil, that setup is called as a secondary circuit. So if the total flux linked with the first coil, it does not equal to the total flux linked with the second coil. Flux linked with the primary circuit is always greater compared with the flux linked with the secondary coil. So some of the flux, it will be loss in the form of leakage. And the last one, to avoid losses due to the eddy current, the core of induction coil and transformer is not constructed as a block but large number of thin strips. Already I told it, we are not ready to use a thick size of the metal, which metal is used to produce the eddy current. We are not ready to use the thick metal because enormous amount of heat energy is produced, and also we cannot get that, we cannot convert that total flux energy, magnetic energy into electrical energy. So for that purpose we are using that number of thin strips. Already I told that thin strips, the symbol strips, or we can use E and I type strips also, we can use it. So if they are asking what are the disadvantages of eddy current, you focus the first 2 points. There is a loss of magnetic flux and loss of the heat energy. We cannot convert that total magnetic field, magnetic energy into a useful electrical energy. Students, now we are going to enter the next topic, methods to producing induced EMF. How we can produce the induced EMF in the particular circuit. Students, our next topic is methods of producing induced EMF. What is meant by EMF? Already I explained that topic in the beginning of the lesson. EMF is called as electromotive force. It's not a force. The EMF is called as a work done in moving a unit charge in a particular circuit. It is a work done to moving a unit charge in a particular circuit. And already you have studied the work done formula in the first chapter. W is equal to V into Q. Using that relation, we can write the unit for EMF. EMF is not a force, it is a work done in a moving charge, moving unit charge in a given circuit. So V. Okay, in the first chapter you studied that V is nothing but it is a potential difference or electric potential. Now we call it by the name of EMF. Using this relation, we rearrange the formula like this: V is equal to W divided by Q. So with the help of this formula, we can write the unit for EMF is Joule Coulomb power minus 1. Joule Coulomb power minus 1, or otherwise simply we can write it as a unit for EMF is volt. So here I write it only the two equivalent unit for EMF. We can write in the various equivalent form. You notice V is equal to the unit for EMF is Joule Coulomb power minus 1 and another one is a volt. So EMF, Now we are going to discuss the source of EMF. Maybe they are asking in 2 mark question. Can you give any example for the source of EMF? The textbook they are given the 4 examples. First one is electrochemical cells. Electrochemical cell. And second one is thermoelectric devices. Electrochemical cell, thermoelectric devices, solar cell, electrical generators. Electrochemical cells and thermoelectric devices, solar cells and electrical generators. These are a few examples, the source of EMF. The source of EMF. Now, we are going to discuss about how will you produce the induced EMF in the closed circuit. We can produce the induced EMF only in the closed circuit, not in the open circuit. The open circuit, we cannot produce the induced EMF. So, methods of producing induced EMF. We know the formula for induced EMF in Faraday's second law. I write the equation induced EMF is equal to minus d phi by dt. The rate of change of magnetic flux linked with the coil is equal to the EMF induced in the particular circuit. If you are concerned the magnitude alone, E is equal to d pi by dt. So the magnitude of induced EMF in the closed circuit is equal to the magnitude of rate of change of flux in the given circuit. So E is equal to d pi by dt. And also we know the formula for pi. Pi is equal to VA cos theta. Pi is equal to VA cos theta. If the circuit it consists n number of turns, we can write the formula for pi. Pi is equal to NVA cos theta. NVA cos theta. You apply the pi value into the given EMF formula. So is equal to d by dt of NVA cos theta. NVA cos theta. So using this formula, we are going to explain the methods of producing induced EMF. We can produce the induced EMF by changing d by dt is change with respect to time by changing the number of turns or the magnetic field linked with the circuit or the area of the coil in the particular circuit, and theta. Theta is nothing but it is the orientation, the relative orientation with the coil, with magnetic field. Orientation, relative orientation between the coil and the magnetic field. So, if you want to produce the induced EMF in the closed circuit, you should change the number of turns in the coil or the magnetic field linked with the coil or the area enclosed by the coil and orientation between the changing the orientation between the coil and the magnetic field. So the 3 mark question or sometimes they are asking the 2 mark question, methods of producing induced EMF. Okay, so in this question you note the one point, by changing, without writing the answer, without that word by changing, you have allotted the mark for the question is 0, because without change we cannot produce the induced EMF in any of the closed circuit. So to produce induced EMF, by change the number of turns or by changing the magnetic field or by changing the area enclosed by the coil or by changing the orientation of the coil, the angle between that coil and the magnetic field. Okay, a relative orientation, the angle between the magnetic field and the coil is called as the orientation of the coil. Okay, so Now we are going to discuss each and every point. So compare the first point, number of turns, changing the number of turns. If you want to produce, you are going to produce an induced EMF in a given circuit, it is possible to produce the induced EMF when you change the number of turns in the coil. It is possible, but it is difficult to change the number of turns in each and every second. If you want to produce induced EMF in the given coil, it is not easy to change the number of turns in each and every second or each and every fraction of second. So it is a possible case, but it is difficult. So we does not consider this case. Okay, we are using only these three variations. So by changing the magnetic field, also we can produce an induced EMF in the coil. We can change the magnetic field. So for this case, we can write the formula like this. Induced EMF is equal to all the remaining terms are a constant one. So take out from the differential N A cos theta. So dV by dt. So if they are given that equation like this, in this case you are going to change. You are going to apply the variation only in the magnetic field, not the area induced by the coil, not the number of turns, not the orientation. You are applying the variation only in the magnetic field. So this formula is related to the second point, by changing the magnetic field to produce the induced EMF in the given circuit. So okay, how will you change the magnetic field? So to change the magnetic field, we have the two separate methods. First one is, we can change the relative motion between the magnet and coil. Okay, we can change the relative motion between the magnet and the coil. If you kept that coil is a static one, if you move the magnet towards and away from the coil like this, if you move the bar magnet or any one of the magnet like this way, we can induce the EMF in the particular coil by changing the magnetic field. Okay, this is the one method. And another one alternative method is like this. Here, if you change the current through passing through the circuit, if you apply a variation in the current, if you consider any one of these circuit like this, if you consider a circuit, now you are going to induce the current, induce the EMF in the given circuit. You apply a current, it varies from 0 to maximum or maximum to 0. If you apply these two conditions, definitely the EMF is induced in the closed circuit. So that is the two way to change the magnetic field in the given coil for the purpose of producing induced EMF. So we can change the magnetic field, we can produce the induced EMF in the circuit. So by changing the magnetic field, we are using these two ways. One is the relative motion, changing the relative motion between the magnet and the coil, and another one is by changing the current, increasing current or decreasing the current in the particular given circuit, we can produce the induced EMF. By changing the area enclosed by the coil. So we discussed the 2 points, and that point is with respect to by changing the area enclosed by the coil. So this first 2 points is related with the 1 mark question, and third point is related with the one important 3 mark question. By changing the area enclosed by the coil, not the area of the coil, area enclosed by the coil, we can produce the induced EMF in the particular given circuit. One of the important 3 mark question. Next we are going to derive the equation for producing induced EMF in the particular given circuit by changing the area enclosed by the coil. Let's see the derivation part. Next topic, induced EMF. The production of induced EMF by changing the area enclosed by the coil. For this case, you consider a fixed metal rectangular frame. In this frame, we have the one conducting rod AB. The conducting rod, it can be slide over through the fixed rectangular plane. This is a conducting rod. So initially, when you fix the rod in this place, we have a one closed path. We consider the closed path as A, X, Y, B. The length of the sliding conducting rod is L. Now we are applying small amount of force to the rod. Then the rod is moving towards the left hand side with the velocity V. V is the velocity of the conducting rod. It is moving towards the left hand side. A, B is the initial position of the rod. So it encloses the area is A, B, Y, X. Initial area. After applying the force, the rod is moving with the velocity V towards the left hand side. And after a particular time interval, now I am taking the time interval dt. At the time interval dt, it travels a distance x. It travels a distance x and reach the final position CD. Okay, so now it encloses the area D, Y, X, C. This is the initial area. And for the final area is nothing but C, D, Y, X. So we are applying the force. The rod is moving with the velocity V towards the left hand side. After a time interval dt, it crosses the distance. Total distance traveled by the rod is X. Now, all this arrangement is placed in a uniform magnetic field. Uniform magnetic field. Now I mentioned the magnetic field, the notation cross symbol. We know that the cross symbol it indicates that magnetic field, applied magnetic field is perpendicular to the plane in inverse direction. This cross symbol it indicates the magnetic field is perpendicular to the plane, the rectangular loop or the pole or the rod. It is perpendicular and it is inward direction. Perpendicular and inward direction. Applied magnetic field is perpendicular. So all this experiment is done in the magnetic field. So the conducting material AB is moving with the speed V towards the left hand side at a distance x in the time interval dt. So initially it has a larger area. So large amount of magnetic field is linked with that particular closed area. If it is shifted towards the left hand side, we know very well that the magnetic field linked with the final area it is minimum. Here area is large, so the magnetic field linked with that area is greater. Here the area is shorter due to the shifting of that rod. The area it will be reduces, so the magnetic field linked with that particular area is also reduces. So field reduces. Definitely some of the changes produced in the magnetic flux linked with that particular closed area. So change in magnetic flux. Change in magnetic flux is nothing but magnetic field is a constant one. We are going to change the area alone. So change in magnetic flux is done with the help of change in area. So here we are applying the change in area. Change in area is nothing but A2 minus A1. Final area minus initial area. Here initial value is larger, so we can apply it like this: initial minus final. The change in area is nothing but the difference between the final and initial area. Which one is greater value? We can take it at first because it is a change in area. We use only the magnitude value. So here we have a larger area in the initial case, very lesser area in the final case. So using this case, the larger area is subtracted from this area. We got the area is A, B, C, D. The area, change in area in this case is nothing but area A, B, C, D. Because this total area is the initial area. This one is the final area. You subtract from the initial area into the final area, we get the area ABCD. So change in area in this case is ABCD. We know the formula for area of the rectangular loop or rectangle shape. It is nothing but length and breadth. So the length of the rod is L and breadth is nothing but, this one is the length, this breadth is nothing but distance travelled by the rod. Distance travelled by the rod, the value is taken as x. So change in flux linked with that closed path is equal to BLX. We know the value of B, it is the applied value, it is given by us, and L also known value. We don't know the value of x. So for alternative x, we are going to replace the symbol x by any other knowing value by using the basic formula. Velocity is equal to traveled distance by time taken. Here we know the velocity of the rod and time taken also we know that dt. So for x we can replace it v into dt. So the equation becomes dy is equal to VL V dt. So you take it equation number 1. Now we have the equation for change in flux in the closed loop, rectangular loop is equal to VL V into dt. In this case, we are going to derive the equation for production of induced EMF by changing the area enclosed by the coil. So induced EMF, the formula is taken from Faraday's second law. It is equal to d by dt. Okay, induced EMF is equal to d by dt, rate of change of magnetic flux. Already we have the value t pi. Here we are going to calculate the magnitude alone. So t pi by dt, apply the equation 1 into this case. So b L v dt divided by dt. Dt will be cancelled. So induced EMF produced in the closed path is equal to V L V. V is the applied magnetic field and L is the length of the conducting rod and V is the velocity of the conducting rod. So all the values are known value. So using this right hand side known value, we can easily calculate the produced induced EMF in the given closed path. Okay, this is one of the 3-mark derivation part, and some of the numerical problem you are going to calculate the induced EMF. Few of the question they are given the value of V, velocity, in terms of kilometer per hour. If the train is moving in the track with the speed particular kilometer per hour, you are going to calculate the EMF induced in the conducting material in the train track. When the train is moving in the track, that time also it produces a minimum amount of EMF. So that type of related question, they are given the data in terms of kilometer per hour. Before you are applying the values into the formula, you should convert all the given data into the SI unit. Here you convert the value into meter per second first. After that you apply the value. In each and every problem, already I told that each and every problem you should convert that given data into the SI unit at first. After that you apply that value into the given formula. Okay. So this is the formula for induced EMF produced in the closed rectangular loop by changing the area enclosed by the coil, and also we can calculate the induced current also. Induced current, the direction of the induced current, it will be taken from the Fleming right hand rule, or otherwise we can easily mention the direction of induced current in the circuit with the help of the right hand cos flow rule. Fleming right hand rule plays the main role. Here we can calculate the direction of the induced current in the closed rectangular loop using like this. This is the direction of the magnetic field, and this folded finger it indicates the direction of the current flowing through the direction. So like this direction clockwise. So current induced in the closed rectangular loop in clockwise direction. Now I am going to calculate the value of I, we have the formula using the Ohm's law. V is equal to IR, or I is equal to V divided by R. Here V is EMF, induced EMF. We know the value VLV. Apply it here. I is equal to VLV divided by R. This is a formula for induced current or producing current in the closed rectangular loop by changing the area. So this is the induced EMF or producing EMF by changing the area. This is the formula related to induced current or producing current by changing the area enclosed by the coil. So how to produce induced EMF in a closed circuit? We can change the number of turns. We can change the magnetic field. If you change the number of turns, if you change the magnetic field, if you change the area enclosed by the coil, or otherwise if you change the orientation of the coil with respect to the magnetic field. So 4 ways are there. In this class we discussed the 3 things. First 2 related to the 1 mark, and second question, third one is related to the 3 mark, and the last 4th one, orientation of the coil with respect to the magnetic field. That question is related to the long answer question, 5 mark part. So we will discuss that topic in the next class. Thank you students. Thank you.